Ladies and gentlemen, good afternoon. It's a great honor for me to introduce Professor Mawhin from the Université Catholique de Louvain. I have known him for about 30 years. We first met in Poland when I was studying fixed point theory with Professor Gorniewicz, precisely in Warsaw. Let me say that since then, Professor Mawhin has been a non-trivial fixed point for me and my research team. I would like to take this opportunity to thank him once again. Today, Professor Mawhin will speak about abstract averaging method and application to differential equations. Please.
Okay, thank you. I have to prepare the screen. This and this. Okay, do you see it correctly?
Yes. Yes.
Yes.
Yes.
Do you hear me?
Yes.
Yes. Okay, so thank you very much for the kind introduction. It's a great honor and pleasure for me to open this webinar, because it's the terminology. It's not very elegant, but which is now universal. Okay, and I hope we shall not have technical difficulties, because it is for me the first time that I am using this technique. The topics I want to speak to you today is rather simple. So it's good to start with a simple thing so everybody can be more sophisticated in the sequence of the seminar. And it is based partly on a joint work with Professor Sid from Vigo in Spain and Professor Zima in Poland. The paper has just appeared in the Journal of Differential Equations. So abstract averaging method, so there is averaging method there, and the averaging method is an old technique in ordinary differential equations. I will recall a little bit of the history. And what is the idea of this method? If you start from what is called differential equation, a system in standard form, which is x dot with a small parameter epsilon will be always restricted to be small, epsilon, tx, and epsilon. You want to study this problem, and so you try to replace it with something hopefully simpler. And you replace the right-hand member by what is called some type of average. And to do this average, you take epsilon 0 in F. So it's the first order approximation because there is an epsilon there. And you compute the average over a large interval of this vector field, of the original vector field. If, of course, this quantity exists, which is not always the case. So if it does exist for every x, you obtain, therefore, an autonomous system, and the idea of the averaging method, or the results, essentially are of two types. Either they are, let's say, quantitative results. You compare, so you obtain an estimate for the difference of the solution of the original system and of the average system on some interval which is large but not infinite. It's of the order of 1 over epsilon. So it's large because epsilon is small. So this is a quantitative type result. And the second type of result you can obtain is some relation between the solution of those two systems, this time on an infinite interval, either R or the positive real number. And then the properties you have in mind are periodicity, almost periodicity, stability, boundedness, and things like this. And the idea which is under the method, in order to consider both questions, is essentially to make a change of variable which is close to identity, going from x to psi, and which will reduce finally your original system.
Professor Mawhin, sorry, excuse me. We
Yes?
can see just the first page of your conference. Maybe you have to.
Okay. So I have to, or maybe to start again to share this thing. Okay. And you think then okay, so maybe.
Okay, now we see the second page.
You see the second page.
Now, yes.
Okay, so it is when I don't put it in full screen. So maybe it's not a good idea to put it in full screen. So I will leave it like this, maybe.
Okay.
Yeah.
Could you try?
Let's try. I try the next page. Do you see?
Yes. Now it works.
Now it works. Very good. So thank you
very much
for informing me, because of course I know my text by heart, so I don't need to read it. Okay. So this change of variable close to identity will reduce the original system to a system which is the average one up to an error of the order epsilon square. And so that's the basic tool. The averaging method has first been used formally, so without any justification, by van der Pol. You know van der Pol equation, so that's this one. And his first idea when he was studying nonlinear oscillator, so with a small nonlinearity, that's the equation of a forced nonlinear oscillator. He was just using the method of variation of constant by doing this transformation, going from y and z to x1 and x2, and then after messy calculation, you get a system, as you say, which is in standard form. In the same way, if you have a free oscillator, in this case, there is no time dependence in the nonlinearity, you want essentially to obtain the orbit in this case of the problem. So you make this essentially transformation from yz to x and theta, which is polar coordinates, if you like. And then you obtain a system like this, but as there is no time dependence, you can still reduce to a single equation by taking the ratio here. And you see again, it's a system which is in standard form, one-dimensional. So van der Pol used those transformations, and then he heuristically, without any justification, replaced in those standard equations the right-hand member by a time average over one period, because in both cases, the system is periodic in t or in theta. So that was van der Pol, and his work inspired there other mathematicians, not directly Fatou. Fatou was independent, so Fatou is the Fatou of Fatou's lemma in integration theory, you know. And Fatou was, in fact, he made his career as an astronomer. And so he was interested in the equation of celestial mechanics, and then interested in a planar system of this type, dy over d tau equal f, and you see the dependence in tau. Originally, f is periodic in this t variable, and because you have this change of scale here, this is called a small period system. But if you make, you come back to the original t from here, then you will get a system which is in standard form. And in a beautiful paper of 28, Fatou essentially considered the non-degenerate zeros of F0, of the average equation of the previous slide, and he proved rigorously then they will provide t-periodic solution of the original system. And second important name is Bogolyubov, a Russian mathematician, and during about 10 years with Krylov, they wrote many papers and monographs where they insist on the formal development and the application to many problems of this averaging method. And in 1945, in a Russian publication, which is not easy to find, Bogolyubov then gave a mathematical justification, which was there then made more publicly distributed in the monograph with Mitropolsky, first published in Russian, but then translated in many languages. And that was maybe the first book with mathematical justification. But in general, the contribution of Fatou had been either forgotten, or when it's quoted, they don't really quote all what he has made there. And really, he has already made everything about the averaging method, almost everything in this paper, on the planar systems, but at the right moment, he says that all this is the same in dimension n, and this is true. Okay, so for periodic solution, the theorem we will concentrate here is essentially this one. And this is the formulation of Fatou and of Bogolyubov. If you have a C1 vector field, which is t-periodic with respect to time, then to every zero of the average vector field F0, this one, which is non-degenerate, so such that the determinant, the Jacobian, is non-zero, you can find a positive number epsilon1, such that when epsilon is smaller than epsilon1, the system has a unique, the original system has a unique periodic solution near zero. Uniqueness is only in the neighborhood of C0. And this solution, when the parameter epsilon goes to zero, the solution goes to epsilon zero. So proofs were given by averaging by Fatou and Bogolyubov independently. And then after, in the 40s and 50s especially, everybody who was proposing a method for the study of periodic solution of systems with small parameter, everybody found his own proof of this theorem, either by using the Poincaré operator or the Lyapunov-Schmidt method, or a variant of it like the Cesari-Hale method. And when you arrive then to the finite dimensional problem, you use they use all the implicit function theorem. So they give different proof, which has a common characteristic, is that they did not give any type of convergent iteration for the solution. You could, of course, obtain successive approximation in terms of epsilon, but in general, you obtain some formal series, or you obtain not a direct iteration. And proof which gave as a bonus a direct convergent iteration were obtained independently in 66 and 67 by Banfi, who was a student of Dario Graffi, this time, and Alan Laser, who just left us not a long time ago. And the characteristic of the Banfi-Laser method, which is based finally on the Cesari-Hale approach, was that if you want the cave approximation for your solution, you have to make two case steps, because it divides the mean value of the solution and the remaining part, and you obtain them separately. So you really need two case steps to arrive to the cave approximation. And I modified their process in 1970, and I just could obtain the cave approximation in case step, which is a little more natural, and this is developed in the book with Rouche on ordinary differential equations. Okay, but one realizes easily that in the case of the periodic problem, you know, in fact, this theorem can be put in an abstract form because, and it was familiar to many people already in those late 60s and early 70s, you have the x dot is a linear operator, and the epsilon f tx is essentially a nonlinear operator multiplied by a small parameter. And in fact, one realizes that all what is required for the linear operator between the two real Banach space, periodic solution, periodic function in our example, is that the kernel, the null space of L, has to be the range of a continuous projector in X. Projector just is a linear continuous operator with square equal to itself. So P square is equal to P. So you need that the null space, which will be necessarily closed in this case, is the range of a projector. And you need that the range of the operator is the null space of a continuous projector in the target space. So that's what we need only for L. And the assumption on F, which will be the nonlinear part of the problem, which will be multiplied by epsilon, is that in fact, by analogy to the theorem, is that you can find a psi0 in the null space of L and a positive number, such that if the following assumptions are satisfied for sufficiently small epsilon, F is continuous, which rests on the ball of center psi0 and sufficiently small radius, and a little neighborhood of 0 for epsilon. And the, I think here there is a dot missing, the F dot of the partial derivative with respect to X is a C1 map, so the function is continuously differentiable with respect to X, and this Fréchet derivative has also some continuity with respect to epsilon at 0. So that's the assumption. So just replace here F by F dot sub X. And the theorem is just exactly the equivalent of the averaging method, a basic theorem for periodic solution. The average this time is just the composition of the projector here in the space Z with F, computed at psi0, this psi0 here, and at epsilon equals 0, and restricted to the null space. So F0 of psi0 is essentially a map from the null space of L to the range of Q. And so the first assumption is that psi 0 is a zero of this, let's say, average vector, average nonlinearity f sub 0. And the second assumption is that the Fréchet derivative, the Fréchet differential of psi 0 as a map from NL into the range of Q, the null space to the range of Q, is a topological isomorphism between those two spaces. So one of the assumptions, finally, is that those two spaces are isomorphic. And so in this case, you have for epsilon sufficiently small and non-zero, this abstract equation Lx is equal to epsilon capital F x epsilon. It has a unique solution x of psi, which is close to psi 0. Uniqueness is only for this solution. There may be other solution associated, of course, to other zeros of f sub 0. And the limit when epsilon goes to 0 of x sub epsilon is equal to psi of 0. So this is essentially a theorem which is the basis. In fact, it's a slightly special case, but not important. That's the theorem which is the basis of the consideration in the paper with Sid and Zima. But in fact, when I prepared this lecture, okay, so maybe let's first try to explain a little bit the situation with one picture. So essentially, all the theorem is in this picture, the statement at least. So you have the space X and the space Z, okay. You have the null space, it is a subspace of X, and you have the range of L, which is a subspace of Z. Okay, L so will go from X onto the range, the range of L onto, and so we consider a supplementary subspace here, which is the given by the range of Q, a supplementary subspace to the range of L. In the same way, a supplementary subspace to the null space to the kernel of L, which is the null space of P. So we have L, which goes from X to here. And if you restrict the inverse, you have, of course, many right inverse to L because L is not one-to-one. But if you restrict this right inverse to having value in the null space of P, then you get a uniquely defined operator, which I will call K. So it will come in the sequel. So this is the definition of K. And the assumption is that you have a psi 0, which is sent by F0, which is this mapping Qn restricted to the kernel and for epsilon equals 0. So it sends Q send this to 0, and then its derivative, which is a linear operator from here to here, is an isomorphism, which is indicated. So that's essentially the assumption of the theorem for the equation. All right. And the proof, in fact, is very simple. The idea is to use the implicit function theorem to the equation Lx minus epsilon f of x epsilon. Okay, and so we already have an approximate solution for epsilon equals 0. Of course, psi 0 is a solution of this problem, but we cannot apply directly the implicit function theorem to it, because if we consider the for the mapping here, if we consider the Fréchet derivative of Lx minus epsilon and x, the Fréchet derivative for epsilon equals 0 will be L, and L is not invertible. So you cannot apply directly to this equation you cannot apply the implicit function theorem. But there is a little trick which will allow us to apply the implicit function theorem. We consider another equation here, a modified equation, if you like, where we replace f, epsilon f, by a convex combination of f with qf of x epsilon. Okay, why not? You can check that when epsilon is not zero, it's a little exercise, the zeros of this new map G are the zeros of the original map. So when epsilon is not zero, we just made it looking more complicated, but we did not change its zero set. On the other hand, when epsilon is zero now, so your equation becomes Lx is equal to Qfx 0. And so L arrives, of course, in the supplementary space for Q. So this is equivalent to saying Lx equals 0 and Qf, the x0, equals 0. And Lx equals 0 means x is in the null space. And so the second equation. So for epsilon equals 0, this is equivalent to this. So this is equivalent to finding a 0 of the average equation. Okay. And then we claim that we can apply the implicit function theorem now to this new equation. And for this, what do we have to check? Just to check that the Frechet derivative at psi 0 and epsilon equals 0 will be an isomorphism. So to see that it is an isomorphism, we just compute it. So it's a little bit of computation, not difficult at all. So this is direct. And so now to compute to prove that it is invertible, we use essentially, we show what is the inverse. And the inverse is finally this expression where we had to split the variable in the original space between the part in the null space and the part in the null space of P with V hat and V check. And in the average, in the target space, we split the function along to the range of Q and the range of L. And this is H bar plus H tilde. And you see that the inverse of the problem here g dot x of psi 0 v equal h is just given by this expression in terms of h bar of h tilde and h tilde here. So you compute it explicitly and you can immediately check by direct verification that it is a continuous mapping. So all the assumptions of the implicit function theorem are satisfied. Now, if you come back to the proof of the implicit function theorem, the only proof essentially which is valid in Banach space is the one which is based on the Banach contraction mapping, then you realize that you obtain also for your solution, the solution we found from the implicit function theorem, we obtain an iteration method, which looks a little bit like a Newton method, but it's a simplified Newton method because here it does not depend on k in the iteration. So that's the classical one. And now we can, from this classical formula, we can go back to the original equation and g of x epsilon equals 0. And things become more complicated looking, but it is essentially a computation where he explicit everything using the explicit formula we have obtained for the inverse of the linear approximation. And in particular, we obtain the first approximation will already give you all the terms. The psi0 is the constant term, but all the terms which depend on epsilon are given here, and the other term are essentially of the order of epsilon square. So that's the associated iteration scheme that we obtain in this case. When I prepared this lecture, I realized, in fact, that I had already stated and proved this theorem was not in the very recent paper here, but 50 years before. And then I had forgotten it. In fact, it was never really published. In some sense, it only appeared in some lecture notes, which were published as an internal report in our university, and they were lectures given in Marseille in '71. And for the ones who know a little bit my work, they know that it was also in this period that I started coincidence degree and all its development. And so I forgot about what was done in this case. And so the Sleeping Beauty only woke up at the occasion of the paper with Sid and Zima, and interestingly gave a result on some contemporary problems. If we come back to the assumption of L, of course, in case L is a Fredholm operator, which is the usual assumption with coincidence degree, that's okay. But in this theorem here, because it's only based on a contraction mapping theorem, there is no compactness involved. And so both the null space and the null space can be infinite dimensional, and the range of Q that can be also infinite dimensional. Okay. And you probably already have guessed what this gives in the case of the T periodic solution. And the interest, in fact, of the fact that those space here can be infinite dimensional is that we can directly work with a system of differential equation in a Banach space, you know. So now we can take X to be in a Banach space, and we immediately will obtain an averaging method in this wider frame. Of course, you see in this case, Lx is x dot, f is associated, the Nemitzsky operator for small f. The kernel will be the constant. The range will be the function which mean value 0. And this is why, of course, the mapping QF becomes the average mapping in the case of periodic solution. We have several choices for the projector, so it's convenient to take, for example, for the projection on the kernel, just to project the periodic function on its initial value, and the remaining part is the difference. And of course, because of this condition here, it's quite natural to take for Q the mean value of operator for the function. And y tilde will be the difference, so will be the function with mean value 0. And in the operator K, it is convenient also to introduce this notation, this special integral, which will be essentially the indefinite integral. But if you do this to a periodic function, it is not necessarily periodic, of course, because there may be a secular term, a term proportional to t, which is associated to the mean value of y. And so in this operation, we subtract this non-periodic term. And so you obtain a primitive of y, which is also periodic. All right. And so with this, we can immediately state a theorem, which is the averaging method for equation in a Banach space for periodic solution. And you recognize the structure here, the usual structure of our averaging theorem. You assume, of course, because you are in infinite dimension, there is no more determinant. So we assume that the Fréchet derivative at xi0, at the zero of the average, is an isomorphism. Okay, and in this case, you have a unique T-periodic solution near xi0, and you can compute it by successive approximation. I say you can, unfortunately, you will only do it if you are forced to do it, because the complication of this innocent-looking formula when you start to apply explicitly to example is rather terrible. I will just give you an example of a first iterate later. So here the bar over some function means its mean value, and all the other, I think all the other symbols have been explained. So that's a theorem, an averaging theorem for ODEs in Banach space. And to give you a very small example, we go back from the Banach space to 2 dimension. We take here, we write the equation with complex notation. So Z is essentially x1 plus ix2, except 2. And we consider this very simple problem. Z dot is equal to epsilon z to the m, an integer, positive integer, minus a forcing term. And yeah. Excuse me? No. Do you hear me?
Yes, yes.
Ah, okay. So the assumption here is just that if you assume that the mean value of the forcing term is non-zero, so it has a non-zero mean value, then your system will have m T-periodic solutions, which are essentially close to and tend to the product of the modulus of the mean value multiplied by the m roots of unity, m complex root of unity. So you have those T-periodic solution. And because it is a very simple problem, well, I think the proof, you will guess it by yourself. We just apply the theorem. The average vector field is this, so the zeros are given by that, and you compute by doing a little bit of complex analysis the determinant, the Jacobian, and you are happy to see that it is non-zero when, in fact, H bar is non-zero. So, and in this case, we are very lucky. We can find a very simple estimate for the first iterate. So this gives all the terms constant and of the order of epsilon of any one of those solutions. So the error there is of the order of epsilon square. All right. The advantage of the abstract theorem is that you can immediately attack a situation which is conceptually not more complicated, but technically more complicated, the case of a nth equation, differential equation of the nth order. And I come back now to finite dimension because all our examples will be in this setting. And so now we have an equation here of it's some nth order linear differential operator with constant coefficients. They are matrices, of course, and equal to epsilon, a function which depends not only on t and x, but also on the derivative up to the order m-1. And in this case, direct application of our abstract theorem gives the following theorem. If this linear part has constant t-periodic solution, because you may not have noticed, so I insist on the fact that there is no term in x here. It goes from the mth derivative to the first derivative. No constant term, and because there is no constant term, the constants are always solution, are always zeros of this, and so they are periodic, of course. So, but what we have to impose is that it has constant, but only constant t-periodic solution, like it would be the case if you had only the x mth derivative. And if you now take the average vector field, is the average over one period, where you take all the derivative here, 0, and epsilon 0, and x psi 0, and you average with respect to t. So it's an average only, let's say, with respect to the x. And if this xi 0 is a 0 of this average and the corresponding determinant, it's a map from Rn into Rn, is non-zero, then we have the usual conclusion for this system. And the proof is absolutely immediate from the abstract theorem, or almost immediate. And this is a theorem which was finally the motivation of the paper with Sid and Zima, because indeed they had application that they had used, that they have solved by the classical averaging method, where only an xm here, it was in fact a second order equation, we will see it, and they wanted to know if it was allowed to add a term in x prime, and this gives the answer. The answer is yes. And this example, which motivated our paper, came from a physical the modelization of a physical phenomenon in hydrodynamics or hydrotechnology, which is the so-called valveless pumping effect, also called the Liebau phenomenon, because the first contribution to this was by an engineer, Liebau, in 1954. And a toy model for this phenomenon is the following one. You have here a pipe which is maybe rather narrow, and then a vase here, you have something which is larger, you know. And if you have some pressure, constant pressure here, of course the fluid will go up to some height in the vase here, in the thing. And the phenomenon is that if you, instead of having a constant pressure here, you put a periodic pressure which has as a mean value the same constant as this, but you make a small oscillation or some oscillation around this mean value, then in fact the level will be higher. So you can have a pumping effect. You have pumped the liquid in here from some height, just without a valve. So that was and this toy model was made by Probst in 2006, and then it has been studied by Sid, Infante, Liao, Probst, Trudy, Wang, Zima, a joint paper of them in various combinations. And Probst has shown, in fact, that the corresponding problem, when modeled, consists in finding the positive t-periodic solution of such a second-order equation here, u2 dot plus au dot is equal 1 over u, e of t minus bu dot square minus c. And A is positive or 0, so there is or there is no damping, but in practice there is damping. B is bigger than 1, C is positive and is related to the ratio between this width and this one. So if C is small, that means you have a very narrow here pipe with respect to the vase, and E is a continuous function. It's immediate to see that a necessary condition to have a positive t-periodic solution is that the mean value of the forcing term is positive. And so the question was, is this sufficient? And it is still an open problem in general, but it was proved by some of those authors that when A equals 0, then yes, it is sufficient when C is small. And in fact, what we will show with the previous theorem is that when C is small and A is equal to 0, and A equal to 0. But we will show that the same conclusion holds for any A here. The way to study this problem is to change this equation into finally some equation to which we will be able to apply the averaging method. So if you make this change of unknown, you write u is equal x to kappa with kappa is 1 over b plus 1, then you immediately arrive to an equation which is of this type. So now the nonlinearity, several things have happened, let's say several good news. The term in u dot square has disappeared. You have a nonlinearity which depends only on x, and with some power, of course. So the singularity needs not to have disappeared, of course, because those coefficients, or some of them, could be negative as well. But okay, the equation looks maybe a little more simpler already. And for this theorem, in fact, or even for a slightly more general situation, you see this situation is essentially a slightly more general situation than this one. Here, we will assume that the C is small, so this is very narrow. And so it becomes a small parameter here. And we put a general or more general t-periodic function R and S, and some more general exponents alpha and beta, which need not to be positive here. So we consider this equation here, and we prove, in fact, that they have a non-trivial t-periodic solution in two situations, either when this ratio is positive and epsilon is a small parameter, it's really small, or this ratio is negative, and in this case, epsilon has to be large enough. Its inverse, which will be the small parameter in the abstract averaging theorem. And in both cases, you have an estimate for the limit when epsilon goes to 0 of x of t epsilon. And the proof is very simple. Well, we rescale, in fact, we rescale x by some parameter mu at the power 1 over alpha minus 1. And so this gives us now an equation like this. But mu was an extra parameter which was introduced, so we can still choose it suitably. And if we relate it to epsilon by this formula, then we arrive to an equation for V, which is mu, which will be, depending on the case, small when epsilon is small or small when epsilon is large. We arrive here to an equation which is with mu instead of epsilon, which is exactly of the type considered in the abstract averaging method for an nth order equation, which m equal 2. And by applying this theorem to this, we just obtain the theorem which is indicated here. And when we come back with this theorem to the special case and then to the special case to the original variable and original coefficient, the result we obtain is that when the mean value is positive, if C is sufficiently small, this problem has a unique positive T-periodic solution and which has this asymptotic behavior. So this is the theorem we obtain, and we are essentially finished. We gave also in this paper other example to a pendulum with oscillating support, to some delay differential equation, to some non-local boundary value problem, in particular one which was considered by Infante, Pietramala, and Tenuta here, which is related to a chemical reactor. And the reference I mentioned to you, so there was this paper of Befi and Laser about the iteration method, the paper by Bogolyubov. The last one, the one paper with Sid and Zima. And this is in this report that I obtained this forgotten theorem, which after all is still used today. And if you want to know more about the averaging method, then you can go to a very old book. Maybe your library has already thrown them out, but well, there are a few more recent. Maybe this one is the most recent to consult now. Okay, so thank you for your kind attention and continue to take care, because I don't want to be the only speaker at this seminar.
Okay, thank you very much to Professor Mawhin for the very nice talk. Now we have some minutes for comments or questions, if I am right.
Yes, I have a question, if you please.
Are there comments, questions?
I have a question, if you please.
Okay, please.
First of all, thank you very much for this nice talk, dear Professor. I was wondering if averaging method can preserve dynamical properties such as conservation of global and exponential attractors. Can averaging method preserve the existence of global and exponential attractors of the system?
So what is your question? You can, the abstract method can be applied to this situation. when you have
Yes,
some dichotomy. No?
So can it preserve the existence of attractors for the system? For more details, if the averaged model has an attractor, exponential attractor, let's say, do we have the initial system have attractor?
As far as I know, no, I don't know that averaging method could be sufficiently powerful to deal with complicated attractors. You know, no.
Okay.
I think in this case you have to use more sophisticated tools like KM or things. No, in fact, your question is interesting because it allows me to make a comment. The abstract version here works particularly well for the periodic case. So when the attractor in the average equation is a singular point, and so your solution approximates this singular point. So this is, and to have it stable, your periodic solution, you need this singular point to be stable, to be an attractor, to be asymptotically stable, to be an attractor. Yes. It still works in the case of a vector field which is almost periodic. But the abstract method I have developed here does not work already for the almost periodic case, because the assumption of the abstract theorem will not be satisfied if you replace everywhere periodic by almost periodic. So it is a shame, but it is like this. And this is just because the derivative between space of almost periodic function does not have the nice property. The linear part, in fact, makes the problem. It does not have the nice property. The projector do not exist. So in some sense, the power of the averaging method is not for periodic solution where other methods work equivalently, but it's most for more complicated situation. But unfortunately, as far as I know, I'm not an expert in this, but I never heard of this. It's not going to work for strange attractors. No. But
thank you.
There are some progress which can be made. Well, you know, strange attractor and chaotic behavior can be related, also can be obtained by the so-called Melnikov function. Maybe you heard about the Melnikov function. So it is when we want to show some transversality into the associated invariant manifolds. And in fact, there is a connection, a direct connection between the averaging method and the Melnikov function. So that would be the way to try to go to an answer to your questions. First, to look the relation with the Melnikov function, and then to see if it can give some light.
Thank you. Other questions, comments? Maybe my question is stupid, but let me ask the same. Do you have some application to partial differential equations?
Okay, yeah, that's also a very good question, and I did not want to say anything during the talk, not to make it too long. But in fact, because if you look to the abstract theorem, because we do not require in this theorem that the null space of the linear part is finite dimensional. It perfectly works, for example, if you take a wave equation which is perturbed by a small nonlinear term. And if you study, for example, the time periodic solution of this semilinear equation, and which, for example, Dirichlet boundary condition on an interval, to take the simplest situation, so one-dimensional space dependence, then the theorem can absolutely be applied to finding such solutions, in fact. The situation in practice gets complicated because when you have to check the condition that of the implicit function theorem, that you have this isomorphism, of course, then you work in the null space. The null space for the wave equation will be a space of function of one variable, essentially. So it's an infinite dimensional space, and the same for the range of Q. And so you will have to check the invertibility of a linear mapping in those space, and they can be difficult, but it can be done. And I plan to do some work. I have some work in process for this. And so there are applications to essentially at least hyperbolic or semilinear wave equation. Yes.
Okay, thank you for the answer.
And also, in fact, the fact that we deal with also ODEs in infinite dimensional space, there are a number of problems in PDE which can also be reduced to ODEs in infinite dimensional space, of course. And this is the interest of the generalization.
Okay, thank you very much.
May I ask a question also?
Of course, Fabio.
Thank you. Thanks. First of all, thank you very much for your nice lecture, and it was really a pleasure to see you and also the other colleagues and friends. It was just a comment related to the question of Professor Marano, because you mentioned also you have an application to delay differential equations.
Yes, yes.
So if your method deals also with the case of infinite dimensional kernel, so perhaps it would work also for neutral equations, because there is a remark in the book of Jack Hale on functional differential equation. The neutral equation behaves like the wave equation, like that.
Exactly. They behave like hyperbolic PDEs, and on the other hand, the retarded differential equation behave like parabolic equation. Yeah, he made this nice remark that I still remember too. Yes, yeah, it's quite possible. In fact, there are already possible applications to neutral differential equation, like the ones I considered with Jack Hale in a paper a long time ago, which are which sometimes he called this a stable neutral operator.
Yes.
And in this case, the kernel is finite dimensional.
No, stavo sentendo il seminario di Mawhin.
Okay.
Hello, oui?
No problem. There was a Professor Pucci, which was speaking, but not for your comment.
Okay.
But okay.
Okay.
Yeah. So in this case, you can state exactly the averaging theorem for this class. Essentially, it's just technically a little more complicated, and so I avoid putting it the lecture. But as you say, probably one could then deal with more general class of neutral delay differential equation. Exactly. Thank you. Yeah.
Thanks to you. Yeah. Thanks.
Other questions, comments? It seems to not. Well, thanks again to Professor Mawhin. Thank you very much.
Thank you for listening.
Virtual.
Good luck our end.
Technically, it was not too bad. Huh? And you were very brave to start with an old lecturer in front of modern techniques. You know, huh? That was really. Juicy was very confident. Huh?
It was perfect. Very nice.
Okay.
Very nice conference.
Nice.
For me, it works very well.
Yes, also for us.
It's a very good system, and I think we are going to enjoy very much the next lectures of the series. Okay.